What's up guys, welcome back to my channel. Today we're going to work on another calculus problem. So this time we're going to try to take the derivative of a function which is actually known as the modulus function. But of course, if we just try to take the modulus function for a certain form, it'll be kind of a little bit boring. So we're going to try to take the derivative of the modulus power function in general. So we actually have the function y equals f of x, which is equal to the absolute value of x to the n power, where n is any integers. So you might ask, well, what happens when both n and x are equal to 0? Would then that be undefined? You're kind of right, but also we can actually think it this way. If we try to make it as a specific case such that n is equal to 0, we will actually have the case that y or f of x is equal to absolute value of x to the 0 power. Well, if x is not equal to 0, we will just have the constant 1, which actually gives us the constant function for x is not equal to 0. So we can just might as well, for this particular case, include x equals 0 in our function to make it continuous. So meaning that if n is equal to 0, we will slightly change our function into f of x equals 2 parts, absolute value of x to the 0 power, which is actually equal to 1 when x is not equal to 0. And when x is equal to 0, we cannot just write in this form because it will be undefined as 0 to the 0 power. So we'll just simply write as 1 so that it will be continuous. And in fact, you will see that the whole function is just going to be equal to 1. And in this case, we have the constant function, and just keep in mind that the derivative is going to be 0 in this particular case. Now, why do we have to spend all the time to talk about this special case? Because now we want to actually find the general expression of the derivative of this modulus function, well, a mix of modulus function and the power function. How are we going to do that? Well, an easiest way to do it is by the definition of the modulus function on the real number or on the real line. We will say that absolute value of some number is equal to the number itself. In other words, we will say that it's equal to x to the n power if either two cases. If n is an even number, or if n is actually an odd number, so n plus 1 will of course be even, where x is greater than or equal to 0 at the same time. And of course, we will actually say it that way because now if we think that when x is less than 0 and n is an odd number, we of course have x to the n power, well, x is negative, and x to the odd power is going to give us a negative value still, such that if we take the absolute sign, we actually need to change the sign or put another extra negative sign to cancel it out. So for the special case, when n is odd and x is negative, we actually need to rewrite the function as x to the negative x to the n power. And for any other cases, we will say that x to it will just be x to the n. Of course, in this case, we'll just temporarily ignore n is equal to 0 case because we have already seen what the derivative of that function is going to be. Then what are we supposed to do? Now, if we try to take the derivative of this function here, then as a piecewise function, we can just take it individually. So in each case, we'll actually get n x to the n minus 1 power, for the first condition, I'll write as condition 1 here. And then for the second case, we will have negative version for condition 2, which is, again, when n is odd and x is negative at the same time. Otherwise, it would just be first case. Now, why do we want to do it this way? Why do we just want to? For most people, we would just leave the answer this way. But like, why do we actually bother doing it? Because in this case, we actually still split it into piecewise function. So our main goal here is not just trying to find out what the result is, but instead we are actually trying to push a little bit further and see if we can pick up the piecewise function and put them back together into one single expression, like what we did for the beginning when we defined the function itself. Okay, now let's continue and see what we can do. So notice that the second case is just a negative version of the first case. We can actually try to focus on the first case at the moment and see what we can manipulate, how we can manipulate that expression. So in this case, we can actually say that n here we know that is either even or odd when x is greater than or equal to 0. Then still, we can try to rewrite the x to the n minus 1 power into the following. We can rewrite as x to the n power minus x by using the property of exponent, okay, of how we define negative first power. Then, of course, similarly, we can rewrite the second case into n x to a negative n minus first power, n power all over x. And of course, for the second case, we don't even have to worry about like if we need to change our condition, since x is always negative, so we're not dividing by 0. Now the problem is actually in the first condition, because again, we might actually have to divide by 0 at some point. Because we, of course, include x equals 0 in our domain here. So for the second condition, we can leave it as it is. For the first condition, we actually need to change it a little bit to x is not equal to 0. Now, what happens if x is equal to 0? Well, in this case, we actually need to think it in the following way. Okay, so what we need to do is we actually need to split into a few more cases, which is when n is equal to 1 and n is not equal to 1. In other words, we actually need to think of the case that when n is 2 or more, or n is negative. But again, if n is negative, x equals 0 is originally not in the domain anyway, because we will never be able to substitute into our original function and define it, even if there is no absolute sign. So that is not a problem. But here we'll just have a problem when n is equal to 1 and when n is greater than 1 in some sense. Now, what does that mean? Here is what we have. So let's try to take this part off and copy whatever we have to the next board. So let's talk about the first condition here, which is actually the main problem that we currently have because of x is equal to 0 case. Now, when x is not equal to 0 case, we can actually combine it later with the second part. When x is equal to 0, we now need to actually consider it this way. I might as well just make a question mark here and see what happened. Now, suppose that we consider the graph of the original function itself. Then, now we already talked about what happened when n is is equal to 0, it will actually provide us the constant function y equals 1. And when n is negative, we will actually need to exclude x equals 0 as part of the domain, just like how we actually need to exclude it without the absolute sign anyway. Then those two might not give us any problem. The cases that actually give us a problem would probably be when we talk about the positive power function. In other words, the polynomial part. So, for example, when we have n equals 1, well, we know that y equals x is going like this, and y equals negative x goes like this. And since we're taking the absolute sign, we always want to keep every single part that is above the x-axis or on the x-axis like this. So here is our function, y equals absolute value of x. Now let's take a look at another example. Suppose that we have n is even, okay, and greater than 0, of course. Then we still have this part here. Of course, we know that it is totally fine to actually ignore the absolute sign, or the modulus sign, and we can just take the derivative and leave it as a previous form of this. Now, why do we have to bother doing this? Well, we'll kind of explain later. Let's take a look at another example. Now, let me rewrite this. Write this out here. This is y equals absolute value of x squared, which is actually just equal to x squared. Now, if we are thinking of the third power, y equals x cubed, it actually ends up like this. But then originally it should go down to the left, but since we're taking the absolute value, we have to actually take it up like this, and it doesn't go like that. It goes like this. And here is our function, y equals absolute value of x to the third power. Now, if we are just trying to ignore the geometry, the algebra here, and look at the shape of those power functions with absolute sign other than the linear function, we actually see that when it's approaching to 0, the tangent line is actually having the slope equal 0 as well. In other words, we actually can claim that the tangent line on 0 is equal to y equals 0. And again, we can actually use the limit definition by taking the left limit from negative side and the right limit from the positive side, and try to see if we can show that limit as x approaching to 0 on either side of the function is actually going to be 0. And also, to show the continuity and show that when we are trying to use the definition of the limit definition of the derivative on a certain point, in this case it will be at 0. Okay, which is, again, you can put it this way. Use h here. Here is what is it? X minus h. X plus h. It doesn't really matter. X. Or you can just say that 0 plus h to 0 over 0. No, over h is going to approach to 0 as well. But anyway, doing the limited definition, you'll be able to find out that for all those modulus power functions, they're actually not only continuous when x is equal to 0, but at x is equal to 0, the function is differentiable, meaning that the derivative exists by the limit definition of the first derivative of a function. And more importantly, you will be able to find out that that derivative is going to be equal to 0. And because of that, we actually can claim it by the following way. If we're thinking it with if we are thinking it as multiple copies of 0 divided by 0, we can kind of redefine it a little bit, or if you don't like using it, which is actually a fair way of avoiding the controversial arguments, you can say that this holds true when x is not equal to 0, and when x is equal to 0, we'll get 0 when n is greater than or equal to 2. Now, what if n is equal to 1? Well, from the graph, we actually see that clearly both sides are linear, so we can just simply find the slope on both sides and see that if it is approaching from the left, we have a negative slope. When we approaching from the right side, we actually have a positive slope. In other words, the two slopes are not the same, and the function itself is not differentiable when x is equal to 0. In other words, we can think that the function is not smooth when x is equal to 0. When we say the word smooth in math, we usually means that the function, or usually we're talking about a function. The function at such point is not differentiable, but it could be continuous like this, meaning that the point exists at such value, and that value is actually the same as when we try to take the limit from any side to approach to that particular value. But we cannot take the derivative and then have the same or have an agreement by taking from different sides. Okay, then when n is equal to 1 and x equals 0, we actually see that the derivative does not exist. It is actually undefined there, because again we cannot get an agreement from the left and from the right. So here is what happens when we are trying to compare for the first case. So now as we try to combine it with the second case, we'll actually get the following. For x is equal to 0, we actually end up with two different results. We can have dne when x is equal to 0 and when n is equal to 1, or when n is actually negative. It's negative. Now, when n is equal to 0 or when n is greater than 2, we agree that x equals 0 is actually equal to, at x equals 0, we actually have the derivative is equal to 0, or n is equal to 0. And again, what does that mean by n is equal to 0 case? It's just a linear, it's just a constant function, y equals 1. Then, of course, as a constant function, when we take the first derivative, we will just get dy over dx is equal to 0. Or we can just think that the slope of the constant function is just equal to 0. So that's why we can just combine the cases together. Now, how do we combine this case and the negative case together? Well, don't forget, we have in this case for two different things. First of all, we're saying that x is not equal to 0. That will actually include both of them. Then for here, we have x is greater than 0 when n is odd, or when for all x when n is even. Of course, when we say all x, we have to exclude 0 case. Then how can we actually combine them back? with the negative sign, where the negative sign is saying that x is less than 0 when n is odd. Okay, we now need to consider the meaning of absolute value or the modulus sign. That since we are saying that x to the n power is gonna be remain as positive for all these cases, we can say that putting the absolute value here is no different from without the absolute value sign. Okay, so in this case, this is the same as here with this condition here. Then for the other condition, when we have negative n times x to the n power over x, that satisfy when x is less than 0 with n is odd. Notice that when n is odd and x is less than 0, of course x to the n power, which is an odd power, has to be negative. And then we will just adjust, we will just have another negative here combined together to make it positive. Then that is actually in fact the same as putting the absolute value sign on the x to the n power term. Because again, in this case, we'll actually force this whole term to be positive on top or in the numerator without changing the sign in the denominator. So we can just put the negative into the x to the n power term and then rewrite it as absolute value sign like this. So now as we actually have an agreement between these two different conditions for a general expression, we can now claim that generally speaking, we have the derivative of the modulus power function is actually equal to n times the modulus power function itself all over x. For x is not equal to 0 in general, which includes all the even case and all the odd cases as long as x is not equal to 0. Good. And that is actually how we get our general expression of the modulus power function. That's it. Pretty cool, huh? So if you enjoyed this video, don't forget to like and subscribe to my channel. Also, turn on the notification bell so that you won't miss any of my new videos. If you have any thoughts or ideas, you can leave your comments down below. I will see you guys in the next video.